Okay, so thanks for the introduction, Vanderlei. Thanks again, as many of the speakers have said, thanks very much to the organizers for this really unique and amazing venue and fantastic scientific content of the meeting. So what I'll be telling you about today is what can roughly be thought of as tabletop experiments and definitely be thought of as quantum methods to probe the existence of new fundamental particles. So I'll start with a quick idiosyncratic review of the status of particle physics, then talk about how we actually look for new particles using small-scale experiments via the electric dipole moments of particles such as the electron. Then I'll tell you in a little bit more detail about our particular experiment called ACME. It's been looking for the electron EDM. And then hopefully I'll have a few minutes to talk about what Luis mentioned, this new effort to look for nuclear EDMs. Most of you have probably heard, after the triumph at the Large Hadron Collider at CERN, the Higgs boson discovery just a few years ago, or actually almost a decade ago now, really completed the standard model of particle physics. It's the complete self-consistent theoretical framework that describes and classifies everything that we've seen in the laboratory about elementary particle physics, has made hundreds of predictions that have been measured often to tremendous precision. Everything fits together in a beautiful package. It's really a pinnacle of human achievement, but we know that it's incomplete. We know this at least from cosmological measurements. So for example, we look out in the cosmos, we see that dark matter is real, but it can't be explained by anything within the standard model. Another thing that gets a little less attention, but is nonetheless clearly missing from the standard model, is a mechanism to explain how just after the Big Bang, when E equals mc squared, the energy of the Big Bang turned into massive particles. It had to do that in a way that created equal numbers of matter and antimatter particles. But when we look out into the universe today, we see that everything is made of matter and essentially nothing made of antimatter. And what's required to explain that isn't present in the standard model. There must be some new mechanisms to explain that. And that's especially relevant to the work that I'll be telling you about. So it's also worth emphasizing to those outside the field of particle physics the tremendous expectation that came along with the advent of the LHC, because there were many, many strong arrows of evidence pointing to the idea that there must be new physics associated with new particles with mass below about a TeV. So for example, particles like that would be very natural candidates to be the constituents of dark matter. Particles like that, if they carried new forces that violate CP symmetry, would also very naturally explain the matter-antimatter asymmetry of the universe. Certain particles like that, particles associated with the theory known as supersymmetry, where every fermion in the standard model has a partner particle that's a boson, every boson in the standard model has a partner particle that's a fermion. These supersymmetric theories would also very naturally explain the Higgs mass being roughly the value that it is. And without these supersymmetric particles, naturally one would expect via radiative corrections that the Higgs mass would renormalize up to extremely high mass scales. So the fact that we see a Higgs boson, that its mass is not terribly high, seem to indicate that there should be some new particles, particularly supersymmetric particles, with a mass below about a TeV. Unfortunately, all of those tremendously strong areas of evidence were wrong. Everything now that we've understood since the advent of the LHC, everything that we've measured says that there appears to be no physics at a scale below about a TeV. So the LHC has looked for particles with masses roughly, depends on which particle, but roughly in the range from half a TeV to 4 TeV, and they found nothing outside the standard model. Giant experiments have looked for dark matter weighed in this mass range, and they found nothing. And as I'll tell you, our experiments have also seen no evidence for new phenomena associated with particles even well above the TeV scale. Something that's not given so much publicity typically is that the fact, so the actual measured value of the Higgs mass of 125 GeV is actually quite a bit larger than expected in supersymmetric models. In supersymmetric models, if the new particles had been at the TeV scale, you would have expected the Higgs mass to be around 90 GeV. That may not sound like a very big difference, but that difference in the Higgs mass between the prediction and the measured value, actually the mass of supersymmetric particles depends exponentially on that small difference. So the measured Higgs mass was actually a big surprise. And all of this has left us with a question. We know there's new particle physics beyond what's in the standard model. We thought it had to be at the TeV scale. Now, all the evidence says that it's not. But what is the mass scale where new physics appears? And unfortunately, there are very, very few clues to that. We know something should appear at a Planck scale where quantum mechanics and gravity have to interact with each other. Maybe at the grand unified scale, but these are so many orders of magnitude away from experimental sensitivity that it doesn't look very hopeful that if that's where new physics appears, we would be able to detect it. But this discrepancy in the Higgs mass compared to what had been anticipated points to the idea that if supersymmetry is right, and there's still some fairly good reasons to believe that, then the new particles associated with supersymmetry would appear with masses of a few tens to perhaps a few tens of thousands of TeV, which is better than 10 to the 19 or GeV, but still very far away from what's possible with an accelerator, the LHC, or even next generation collider experiment. So now let me tell you about how we're able to actually explore that range of masses, or at least will be in the near future. So we're looking to see if particles, for example, an electron or a proton, have an electric dipole moment along their spin. And you can imagine this cartoon picture. If you have an electron that's a perfectly spherical ball of charge, superpose with it an electric dipole moment, a separation of positive and negative charges. The positive charge will slightly cancel the negative charge and make a little divot on one end of the electron, and the negative charge will make a little bump on the other side of the electron. If all electrons have the property that they have this electric dipole moment in the same direction relative to their spin, then if you take a movie of the world of those electrons, run the movie backwards, you would see a situation where the electric dipole moment, which is the static charge distribution, is now oriented in the opposite direction to the spin, which reverses when you change time. So if particles, the electron or any particle with quantized angular momentum, has an electric dipole moment along its angular momentum axis, then that means that time reversal symmetry is not a good symmetry of nature. And in relativistic quantum field theories, which is our only known description of particle physics, time reversal violation is equivalent to what's known as CP violation. I won't try to explain that, but just say those two things are equivalent, and I'll use them interchangeably. Okay, so what does that have to do with new particle physics? Well, we can connect particle physics to a possible electric dipole moment of a particle like the electron by recognizing that we already know that new particles affect the electromagnetic moments of the electron, specifically the magnetic moment. So in the Dirac theory, a bare electron is a structureless point particle whose G factor is exactly 2 and whose electric dipole moment is exactly 0. But we know, now since the 40s or the 50s that according to quantum electrodynamics, the electron is constantly spitting out and reabsorbing virtual photons. And that process, the sort of cloud of virtual electrons that follows the electron everywhere, corrects the magnetic moment. It makes the G factor not exactly 2, but a little bit bigger. And this is just the simplest, most special case. But in fact, every particle in nature that the electron can interact with is constantly blinking in and out of existence in a virtual cloud that surrounds the electron. And every one of those particles in the virtual cloud affects the magnetic moment. It affects the G factor. So for example, if the electron virtually emits a W boson virtually turns into a neutrino and then recombines into an electron. That changes the magnetic moment. It can also happen with particles that don't connect directly to the electron, such as quarks, via what's shown here, a two-loop diagram, which is a second-order correction. In these sort of loops, heavier particles give smaller effects, scales like 1 over their mass squared, and more loops corresponds to a higher order perturbation theory. So the standard model of particle physics includes time reversal violation, includes CP violation, and it predicts that the electron should have a non-zero electric dipole. However, the predicted value in the standard model is incredibly small. It requires a 4-loop diagram, so fourth order perturbation theory. It requires the heaviest particles in the standard model, the top quark and Z and W bosons, and it requires, there's actually a symmetry in the standard model that makes all the different diagrams of this sort that can contribute to the EDM cancel each other to many decimal places. So in the standard model, the electron EDM is not zero, but it's incredibly small. By contrast, in theories that include new physics beyond the standard model, new particles, and also include new interactions that violate CP symmetry or time reversal violation, these can give much bigger effects. In many of these theories, the EDM is induced at a single loop level, and with very natural assumptions, you can do a sort of dimensional scaling argument and find that the mass scale of new particles in this sort of diagram that are being probed, based on the current best limits for the electric dipole moment, are up to masses of about 50 TeV. And this should be compared to the Large Hadron Collider is only able to detect particles up to a couple of TeV at best. So the effect that we're looking for, these EDMs are fantastically small. To give you a sense, an electron in quantum field theory is an absolute point particle, but this cloud of virtual photons that surround it has a finite size. It's about a femtometer. If you scale that up to the size of the Earth and ask how big an electric dipole moment would we have been able to see in our experiments so far, it would have been equivalent to taking a slice 1 nanometer thick off the southern hemisphere of the Earth and pasting it on the northern hemisphere. But of course, that's with an electron, not with the Earth. So these are fantastically sensitive measurements. The principle for doing them is surprisingly simple. We start with some electrons, we spin polarize them, for example, via optical pumping with polarized light. If we polarize them in the sideways direction, we can think of that as a superposition of spin up and spin down. For technical reasons, we apply a magnetic field that causes the spins to precess around the magnetic field, or equivalently causes an energy splitting between spin up and spin down. To look for an EDM, we apply an electric field parallel to the magnetic field. That'll cause the spins to precess faster if they have an EDM, or equivalently cause the Zeeman splitting to get bigger. Then we flip the electric field back and forth, and look for a correlated change in the spin precession frequency or the Zeeman splitting. Same thing. This makes it possible to write a very simple figure of merit for statistical sensitivity in these experiments. It depends on the size of the energy shift divided by the energy resolution, and that's proportional to, sorry, I have some font issues there, but it's proportional to the size of the electric field that you apply. It's proportional to the coherence time of the spins. It's proportional to the total number of events that you can detect in your experiment, which is a counting rate times an interaction time. Interaction time is a constant of nature determined by how long the graduate students are willing to sit in the lab and flip the electric field back and forth. So the trick that we've employed that's really allowed us to make very rapid progress over the last decade or so is to embed our electrons inside a polar molecule. For example, we use electrons in thorium monoxide molecules. Inside these molecules, due to a subtle relativistic effect, it turns out the electric field acting on the electron or on its electric dipole moment is about 80 gigavolts per centimeter. So that's roughly 6 orders of magnitude stronger than a field you can apply in the laboratory, but the electrons feel it when they're inside a polarized polar molecule that's sufficiently heavy. And molecules also give a similar enhancement for nuclear EDM, not just for the electron EDM. So let me tell you briefly about ACME, the second generation of ACME, performed by this amazing team of students and postdocs, together with my PI colleagues, Jerry Gabriels and John Doyle. John from Harvard, Jerry used to be from Harvard, now at Northwestern. I won't go into much detail, but basically we're able to use this molecule and a series of lasers to spin polarize the electrons and then probe their final direction after they interact with the electric field. The molecule has some additional structure that's unlike anything in atoms that's been proven very useful for suppressing systematic effects and noise of various sorts. In particular, it's possible to prepare molecular states where we can make a superposition of electrons spin up and spin down, where the molecule is polarized in one direction, and then without changing the electric field, we can prepare a different set of states where the molecule polarizes in the opposite direction. That reverses the electric field acting on the electron without us having to reverse the electric field in the laboratory, which proves very powerful and useful. The actual experiment is based on a molecular beam. We have a cryogenic molecular beam source that shoots molecules from left to right. We apply some lasers to perform optical pumping that cools the rotational motion. The molecules then experience a series of lasers that spin polarize the electrons. They fly through a region of parallel electric and magnetic fields as described. And then finally, we use the interaction of the electrons in the molecule with polarized laser light to determine their final spin direction. This is what the lab looks like. Notice the scale of 0.001 kilometers. That's so you can compare it to the Large Hadron Collider. It fits in a room about a third the size of this room. Here's some typical spin rotation fringes, just to show you we can actually take data and tell which direction the spins are pointing at the end of the experiment. The data is quite boring. It's a histogram. The work product at the end is a table of systematic errors. And I won't go into much detail there, but just to say, back in 2018, we were able to get a limit on the electron-electric dipole moment as units of charge times distance. Our limit was less than 1 times 10 to the minus 29 e-centimeters. Now, just this past year, our friendly competitors from Gilla, Eric Cornell and Jun Yi, published a new result that's about a factor of 2 more sensitive than our ACME result. Again, they found a result that was consistent with 0, but set a limit about 2 times better than our prior limit, with an extremely different experimental system with completely different systematics. So it's gratifying we're getting the same result, but ungratifying that we're both getting 0. We're now working on the 3rd generation of ACME, the same team of old folks, a bunch of new young folks and new collaborators from Okayama University in Japan. Here, the experiment is basically the same, but we're using an electrostatic lens to make use of more of the molecules. We've extended our interaction time by a factor of 5. We've improved our detection efficiency and made a bunch of technical improvements. The bottom line is we're anticipating within the next year and a half or so a 30-fold improvement over our prior experiment, so more than a factor of 10 beyond the recent Gilla result. So what's amazing about these experiments is in certain ways they're extremely low-tech. They look nothing like the kind of atomic clock or quantum simulation experiments that we've seen in the last 2 days. So what we would like to do is to start to employ some of the more modern methods of atomic physics, apply them to molecules, which has only recently become possible, in order to get much longer coherence times while maintaining high enough statistics. So as Luis mentioned, we're now embarking on a new experiment where we will borrow the techniques that were pioneered by Debbie Jin and Jun Yi at Gilla, then the Innsbruck group, and now, Emmanuel and Martin and many others, over a dozen groups in the field, have learned how to take cooled and trapped alkali atoms, combine them coherently to form bound molecules in their ground state, while adding no entropy to the system, no heating. And this allows you to make large samples of ultra-cold optically trapped molecules. And the results are quite amazing. Already groups have demonstrated nearly 10-second nuclear spin coherence times. More than 10 to the fourth molecules has become pretty routine in the field with high fidelity readout of the spins. So what we're going to take advantage of is the fact that in certain heavy radioactive nuclei, the electric CP violating interactions between nucleons can give rise to a nuclear electric dipole moment that's enhanced by about a factor of 1,000 if the molecule has this, or sorry, if the nucleus has this funny pear shape. There are only a small number of very heavy radioactive nuclei for which this is true. One of them is an isotope of francium. And we intend to use the techniques that Luis talked about to cool and trap francium atoms, and then combine them to form a molecule with a silver atom. Silver is special in that it has an alkali-like structure. It's laser coolable. It acts for most purposes just like an alkali, but it also forms strong ionic bonds that are what you need to have the large effective field inside the molecule. I won't go into many details about this, but the bottom line is we're now starting an effort in collaboration with Luis, collaborators at Triumph, Waterloo, and elsewhere to get this idea off the ground. And as Luis mentioned, we're projecting, if we can only get the same parameters in francium silver that other groups have gotten in bialkali molecules, we're projecting 1,000-fold improved sensitivity with potential for dramatic improvements in the future. And I'll just leave this with my last slide. So this is a slide of progress in looking for nuclear EDMs as a function of time on the x-axis, and also on the y-axis on the left, it shows the mass scale that's being probed. The hatched line in the middle is what the LHC is able to probe, and the bright purple stars going up to the right there are what we're projecting in terms of the first couple of generations of sensitivity with this new approach using trapped francium silver molecules. And what's remarkable is it's not crazy to think about reaching the limit of the prediction of the standard model, which would allow us to probe energy scales of nearly 10,000 TeV within the next couple of decades. So we find this very exciting. We think there's a chance to really discover something. And thanks for your attention.